Hey guys, it's OpenQuant, ready to solve question number 8, false positive. So in this question, we have a disease with an incidence rate of 2%. We're also told that the false negative rate is 10% and the false positive rate is 1%. And we're asked to compute the probability that a person who tests positive actually has the disease. So before we begin, let's note down this metadata using our own notation. So we'll say that D is the event that a person has the disease, and P as the event that a person tests positive. And with these two events, we can begin to note down the probabilities given to us in the problem statement. So the first would be that a certain disease has an incidence rate of 2%, meaning that the probability that a person has the disease is 2%, 0.02. The second piece of information is that the false negative rate is 10%. So just a reminder, a false negative is when a person shows negative, they test negative, but they're actually positive. So this expression is they test negative given that they actually do have the disease. So that's negative P prime, D prime. Just to go back a little bit, so D prime would be correspond to the event that a person does not have the disease, and P prime that a person tests negative. So back here, so the probability that a person tests negative given that they do actually have the disease, aka a false negative, is 10%. 0.10, and the probability of a false positive is 1%. This is given to us in the problem statement. So translating that to our mathematical notation would be that the probability that they test positive given that they do not have the disease is 1%, 0.01. And from this metadata we can actually compute three new pieces of information, and that would simply be by taking the complement of each of these three respective events. So the probability of D prime, the probability that someone does not have the disease, is 1 minus 0.02 or 0.98. Again, this is simply by the complement rule. By similar logic, the probability that a person does test positive and they do have the disease, so this would be an accurate test result, is 1 minus 0.10 or 0.9. So again, this event right here is the complement of P prime given D. And that's simply because we're conditioning upon the same event, but what we are solving for is the complement or the opposite of. By the exact same logic, the probability that a person tests negative given that they do not have the disease, this would also be an accurate test result, is 1 minus 0.01 or 0.99. And with this metadata set in place, we can begin to compute the probability that a person who tests positive actually has the disease. So just to recap, this problem is asking us to compute the probability that a person who tests positive actually has the disease. So what's the probability that they actually have the disease given that they test positive? What is the probability that they have the disease, or just D, given that they test positive? So that would be the expression we are asked to compute, translate to the notation that we've derived above. So we can start this again with Bayes' rule. When you see conditional probability, think of Bayes' rule. And this is simply equal to the probability of P given D times the probability of D divided by the probability of P. And this expression was simply determined by, it's the definition of Bayes' rule. It has an alternative definition where we have the probability of P and D, or intersect D divided by probability of P. But for our problem, this formula is easier to use simply because we've already solved for some of the terms in the numerator. So we'll begin to expand that and solve it. So we know that we know the probability of P given D. It was part of the data that we have solved for in our initial problem statement. It's right there, and we know it's equal to 0.9. Similarly, we also know the probability of D, the second term in the numerator, right there, and it's given to us in the problem statement as 0.02. We do not, however, know the probability of P. That is not information that was given to us, and we're going to have to solve for that by different means. So to solve for the probability that a person tests positive, the probability of P, we're going to use something called the law of total probability. And before I get into that, I would just like to draw a little illustration to clarify exactly what it is that we'd be solving for. So in this case, we have two events that are not necessarily independent, P and D. So we'll say that this probability is P, and that's what we're trying to solve for. And let's also say that P is stratified by different subsets of D. So we'll say this is, this is just a hypothetical. We'll say this is D1, this is D2, D3, D4. To solve for probability of P, in this case, it would be analogous to the probability of P and D1. That would be that area right there, plus the probability of P and D2. That would correspond to this area, plus P and D3, all of that right there, and fourth probability of P intersect D4, this last little subset. So as you can see, these four individual terms summed together give us the probability of the event that we are trying to solve. So this is just the law of total probability illustrated in action. So that way we can understand what it is that we're trying to solve for as we begin to use the data that we've found from the original problem statement. So I'm just going to leave this illustration right up there for future reference. So now back to our problem. We're trying to solve the probability of P, the probability that someone tests positive. And in this problem, we know that such an event is split into two cases where the person either has the disease, D, or D prime. So we can say the probability of P and D plus the probability of P and D prime. We also know from the definition and equations regarding conditional probability that this is equal to the probability of P given D times the probability of D. This expression is equal to that expression. For the second term, probability of P given D prime times probability of D prime. Now we have four terms, 3, 4, all of which we know the value of, all of which we have the value of from our metadata derived from the original problem statement. So now we can begin to solve for this expression. Probability of D right there times the probability, the probability of P given D times the probability of D is 0.9 times 0.02 plus right here probability of P given D prime right there, 0.01 times probability of D prime right there, 0.98. So 0.01 times 0.98. So now from this we can get our total probability of P. This is what probability of P is equal to, and we can substitute this back into our original expression derived from Bayes' rule to get the probability of D given P is equal to 0.9 times 0.02 divided by, and I'm just going to copy this entire expression right here, divided by this entire expression right there. So this is our answer, that this entire expression, and with the use of a calculator I've found that it's equal to 0.647. So right here is probably what the expression that a you would be expected to come up with on an interview, and with a calculator we can come up with the actual probability. It's around 64 hundredths.